but I think I will start. I prepared few tasks ahead of the consultation, so I will just go through them and explain what steps I took, and I did mostly from the first midterm. So yeah, three from the first midterm and one from the second. So yeah,
Okay.
the first one is this determine the remainder if we divide 7 to the power of 3234 by 80. When we get a task or a problem like this, it usually means that we need to use Euler-Fermat because it's like something to the power of, and it's a very big number that we can't calculate by hand or like not even with a calculator. So it usually means that yeah, we have to use the Euler-Fermat. And the Euler-Fermat theorem says that a, so an integer as a whole number to the power of phi n, phi is the Fermat function, is congruent to 1 modulo n. If the modulus, so n, and a, which is right now here, their largest common largest common divisor is 1. If it's true, or like, so if this is true, then we can use this theorem. But what is phi n is the Fermat function, and basically the Fermat function says basically the Fermat function is how many prime numbers are there between 1 and the number that's here. So right now it's n, or here it's 80. But how do we calculate the number of prime numbers between a number and another? Well, for one, you could actually try to count them, but I suggest that you don't, because it's quite kind of long. Instead of that, we also know that this phi n can be calculated if we take a number prime number multiplication, let's say that, and we use this format of like a to the power of k minus a to the power of k minus 1, and you multiply this by b to the power of, I don't know, l minus b to the power of l minus 1, and you do this until there are no more primes that you need to factor in. So in this case, both a and b are prime numbers. So knowing that we can use the Euler format, because 7 and 80, 80's biggest common divisor is 1, then we can calculate the phi function. We calculate it by finding the prime number multiplication form of 80, which is like we first try to divide it by 2, we can divide it by 2, so we try to divide, we get 40, we try to divide 40 by 2, we get 20, we try to divide 20 by 2, we get 10, we try to divide 10 by 2, we get 5, we try to divide 5 with 2, because that's the first prime number, we can't. We try to divide it by 3, we can't obviously. We try to divide it by 5, because that's the next prime number. We can. So we know that 80 equals 2 to the power of 4, because 1, 2, 3, 4 times 4 multiplied with 5, because we only have 5 one time here. So this is the form we are looking for. Using that, we take 2 to the power of 4 and subtract 2 to the power of 3, which is 4 minus 1, and multiply it by 5 to the power of 1, minus 5 to the power of 1 minus 1, which is 0. And obviously we know that 2 to the power of 4 is 16, to the power of 3 is 8, 16 minus 8 is 8, 5 to the power of 1 is 5, 5 to the power of 0 is 1, because every number to the power of 0 is 1. We multiply them together, and we get 32. Now we know that phi 80 is 32. That this calculation is like one of the most important part of this Euler Fermat theorem and function, this phi function. Now we know that 7 to the power of 32 congruent 1 modulo 80. But how does it help us? Because we have 7 to the power of 3234 here, not 7 to the power of 32. Well, we can do a few things with modulus, or like, yes, congruent values. We know that 3234 is equal to 101 times 32 plus 2. And we use this form because it has 32 in it. It's like we calculated by just dividing this number by 32, we get 101 plus 2. So like we are trying to find the closest division number that we can divide it with 32, and then add the extra remainder to it. Now that we know that we can use this, we know that 32 times 101 plus 2 is equal to this. We can use it. You can raise something to the power of raise this whole modulus to the power of 101, and it will stay true, because you are basically just multiplying itself 101 times, and when you are multiplying congruent values, it will stay true. So using that, we can write this this down and know that it's true. So 7 to the power of 32 to the power of 101 is congruent to 1 to the power of 101. But 7, but 32 to the power of, but 7 to the 32 to the power of 101, we know that A to the power of B to the power of C equals A to the power of B times C. So using this, we know that yes, 7 to the power of 3232 congruent 1, because 1 to the power of 2, 3 or any number stays 1. And we got, as you can see, we got really close to this number. All we have to do is multiply the whole expression with 7 to the power of 2, because we also know that A to the power of B times A to the power of C equals A to the power of B plus C. And using this theorem, we get that 7 to the power of 3234 congruent 7 to the power of 2, which is 49 modulus n, modulus 80. And thanks to that, we got that if we divide 7 to the power of 3234 divided by 80, we divide that, then we get 49. 40. Yes, 49. Obviously, for this to work, the important thing that you will need to look at the midterm is that first you have to make sure that you can use the Euler Fermat. You can do that by checking if the largest common divisor is 1 between n, which is the modulus, and a, which is like the number, in this case 7. Yes, so 7 and 8 is largest common divisor is 1. And also, if you don't know, if you can't tell it by looking at it, you can't tell it if it's true or not by just looking at it or by glance. You can just calculate it kind of easily over the same using the same method we used here. So like this, we take 80. We already know that it's like 2. We divide it by 2, we can, so it's like 80 divided by 2 is 40. We divide it by 2, it's 20. We divide it by 2, it's 10. Divided by 2, it's 5. Divided by 5, it's 1. So 80 equals 2 to the power of 4 times 5. And now we take 7. And 7, you try to divide it by 2, obviously you can't. Then 3, you still can't. 5, still can't. 7, you can divide 7 by 7, obviously. You get 1. So you know that 7 is equals 7 times 1 or times 1, it doesn't matter, but 7 is obviously a prime number. And using that, you can calculate obviously the smallest, largest common divisor. It's like 80 and 7th largest common divisor can be calculated by taking the similar or like the same parts of both multiplication. So in the So basically, those numbers that you can find in both here and here. Right now, there is no number like that, so we know that this is true. So the smallest, the largest common divisor is 1. If we took another number, let's say 4, you start the same process. 4 divided by 2 is 2. You write down 2. 4, 2 can be divided by 2, and it's 1. You finish it. Obviously, you can't go further because it would be just like 1, 1, 1, 1, 1, 1, 1 everywhere. You write down that 4 is equal to the power of 2. Now, in this case, when you are calculating the largest common divisor, you take into account those numbers that you can both find here and here. Right now it's 2. So 2, but 2 is technically 2 is here technically 4 times, and it's 2 times here. So you take the smallest power of. So in this case 2. So 2 to the power of 2, and that's 4. And now we know that the largest common divisor between 4 and 80 is 4. And if here it wasn't 7 but a 4, then we could not use the Euler-Fermat, because Euler-Fermat is only true when this fact is true. So like they are relative primes to each other. Yes. Yeah.
Then how would we continue doing it?
If
GCD is not 1.
if we can't, yes, if you can't use Euler-Fermat, then the best course of action would be like give me a second. But I think then the best course of action would be seeing if first we can So then we see if we can divide the whole equation with that number. So can we divide no, sorry, wait. No, if you can't use Euler-Fermat because of this, then you can try try calculating it by raising it to the power of 2 continuously. What I mean by that is like let's call a line. Yeah, let's draw a line here. So then we say 4 to the power of I don't want to go up to that number, so 257 congruent something, obviously modulo 80. And when using this obviously right now we can't use Euler-Fermat. So instead we say that for congruent for yes modulo 80, that's obviously true, and then we raise it to the power of 2. So 4 to the power of 2 is congruent 4 to the power of 2, which is 16 modulo 80, and then we do it again. Now it's 4 to the power of 2 to the power of 2, which is 4 to the power of 4 congruent 16 to the power of 2 modulo 80, and this, if we calculate this 16, which is, give me a second, of course 256, and now we know that 4 to the power of 4 congruent 256 modulo 80. However, obviously 256, you can subtract 80 from it. So 256 minus 80.
Why do we subtract from it?
We subtract it because 256 equals to 3 times 80 plus, give me a second, plus 16. And because of how it's like making a congruency simpler, more simple by yes, by subtracting the modulus from this number if we can, because it's not like it's not a function. So like, give me a second. So it's when we are talking about congruencies, it's like 4 is congruent, 4 to the power of 4, it's like, or like simply 4 is congruent more with more than just one number. So 4 is congruent with, give me a second, now I'm just, give me a second. So 4 is congruent with 4 modulo, I don't know, 5, but it's also congruent with 9, because if we are modulo 5, because if we are dividing 4 with 5, we get 4, we get 0, and the remainder is 4, and 9, if we divide it by 5, we get 1, and the remainder is 4. So more than one number, obviously, because it's like, it always takes a form of like k times the modulus, which is right times 5 plus 4. And as you can see, if we use that here, so like k, which is right now 3, times 80, which is the modulus, plus 16. So we are making it simple. We are making basically this 256 simpler. more simple. Because of that, we have right like now 4 to the power of 4 congruent 16 to the power of modulo 80, and now we have a much smaller number to work with. So like, because now we are going to raise this whole expression to the power of 2 again, which will be 4 to the power of 4 to the power of 2, which is 4 to the power of 8, congruent 16 to the power of 2, which obviously we know that we already know that 256 modulo 80, and instead of like having to calculate 256 times 256, no, 256 to the power of 2, yes, 256 times 256. Instead, we had just had to calculate 16 to the power of 2, which is 256, and we use the same trick again of like, that's 3 times 80 plus 16, and because of that we can just like cross out the 3 times 80 and we just get 16, and now we know that 3 to the power of 8, and we raise it again to the power of 2, which is 4 to the power of 16, congruent with 16 to the power of 2, which is again 256. I just like I just randomly choose these numbers, so it's really funny that it's that simple calculation. It should have been a bit more difficult, but yeah, basically right now we are just like getting all the way up to like 16 times 2, and then which is like 32. And it will be stay 16 and then 4 to the power of 32 times 2, which will be 64, and the modulus will still be 16 because of this like pattern that we just got here. You won't always get a pattern. Sometimes you actually have to calculate every single time, but usually it's like a smaller number, so like a simple multiplication will help you. And then obviously 4 to the power of 64 times 2, which is 128, and then 4 to the power of 128 times 2, which will be 256. So because of this continuously raising 4 to the power of 2, and also at the same time making sure that we are always making this side's expression more simpler. We got that 4 to the power of 256 congruent 16 modulo 80. But obviously I asked the question of like 257. What? So like what's its remainder if we are dividing it by 80? All we have to do is just like give a second, multiply it by 4, and then we know that 4 to the power 257 congruent 4 times 16, which is I hate calculating like in my head. Is 664? Yes. And thanks to that we got the answer. So like 4 modulo 4 to the power of 257 equals by congruent 64 modulo 80. If it was like, I don't know, 4 to the power 200, just a second to make my 260, let's say, then we can do that similarly, or like not similarly, exactly the same way. We get to this point of like 2 to the power of 256, and then it will be we see that 260 is 256 plus 4. We go back like here, 4 to the power of 4 to the power of 4 congruent 16 would do 80. So 4 to the power of 256 times 4 to the power of 4 is congruent with 16 times 16, which is 80, with 80. And obviously, like this 4 to the power of 260, if we use the theorem of like a to the power of b plus to the power of c, so not plus multiplied by a to the power of c is a to the power of b plus c. And obviously you can do that, so 16 times 16, which is 256, and you then modulo 80, and then you use the same 3 times 80 plus 16. You basically cross out the 80, and then you get the 260 congruent with 16 modulo 80. So if you can't use the Euler-Fermat, you can use this way of solving it. And basically, if it's not like the easiest is always if it's like a power, if up here, so this number is power of 2, is a power of 2. If it isn't, then you look for the closest power of 2, and then you just take it, take it into the parts of power of 2. So like, for example, let's say a random number 263 is like the closest is 256 plus you still have 7, then 4, and you have 3, then 3 is like 2 plus 1. And the important thing is this, the thing is that all these numbers is like 2 to the power of, that's 8, not 8, 8, right? Yes, 8. That's 2 to the power of 2, that's 2 to the power of 1, and that's 2 to the power of 0. And because of that, you calculate all of them while you are getting to this number, or like this number, and then you go back, check what those are, and you just multiply them together. This way of solving a problem is not just like for this. There are some exercises that will ask you to use this method and not the Euler-Fermat or any other way. For example, I think I just found one of them somewhere. So rewriting. No, let's stop that. Yes, so for example, there is this this one. Use the algorithm we learned to determine the last 2 digits of 4 to the power of, it's not not 449, it should be 4 to the power of, just like it can't really copy that, but when they are talking of like use the algorithm we learned, they are talking about this. So if we want to solve that, 4 to the power of 49, and because they are asking for the last 2 digits, that's like that equals, or like that correlates if we are looking for 4 to the power of 49 modulo 100, because if we divide something by 100, the remainder will be always the last 2 numbers, because we basically cross everything out before it. And yeah, if we want to calculate with the last method, 4 to the power of 1, let's go at 4 modulo 100, and then it's like you raise it to the power of 2, 4 to the power of 2, 16 modulo 100. We right now can't really make it more simpler. 4 to the power of 4 is 16 times 16. How much was it? 256. That's 56, or like, yes, 256 modulo 100, which is 2 times 100 plus 56. You cross this out, so it's like just 56. 4 to the power of 8 congruent 56 squared, which is
3,100.
yes, 36 modulo 100, and that also equals to 31 times 100 plus 36. So you just cross this out. So 4 to the power of 8 congruent to 36 times 100, and you continue it selected. 4 to the power of 16 congruent 36 to the power of 2, which is 1296 modulo 100, which equals to 96, or like correlates to, and then 32 congruent 96 to the power of 2, which is 9216 modulo 100, which is 16. We got back to 16. And now the original question was 4 to the power of 49, and 49 equals to 32 plus 17, but 17 is like not a not equal to 2 to the power of something, but 16 is, so plus 16 plus 1, so it's like 4. That's 2. 32, it's like, yeah, that's 2 to the power of 6, right? 5. No, the 2 to the power of 5, that's 2 to the power of 4, that's 2 to the power of 0. And because of that, we know that 4 to the power of 32 times 4 to the power of 16 times 4 to the power of 1 congruent with 3216 times 96 times 4. yes, because we all calculated that this, and we just have to like then multiply them together. So 16 times 96 times 4, that's 6144 modulo 100, which is like 44. And thanks to that, we got the last 2 digits. It will be 44. Because 4 to the power of 49 congruent 44 modulo 100. So yeah, that's how you use this method. For and obviously for it, it's a much better example because the answer wasn't 16 always. It was like, yeah, obviously always a different number, like 16 here, 96 here, and 4 here. But then in the end, we just multiply them together all the same, and then make the whole expression more simpler. Yeah. The second second one I choose is this. How many integers are there between 1 and 2021, which give a remainder of 18 when divided by 63 and the remainder of 34 when divided by 91. So when there is task like this, we first always like write down what it actually means in math, basically in math language, let's say, in math. So like how you can how you translate it to actual numbers and theorems. So x, if this number exists, so it's, let's say, any number that can be, this is x, and this x then congruent with 18 modulo 63, and x also need to be congruent with 34 modulo 91. This obviously because of this, and this part is because of this first part of like 18 when divided by 63. This first line of like between 1 and 2021 will come in later. And right now we just need to focus on this, finding those numbers that that make this equation true. Now from this, x equal x congruent with 18 means that any x number can be written down like this. So 18 plus k, so k times 63. That's thanks to the nature of congruences. With this not function, with this theorem, yes, let's say theorem, you can find all of the numbers that congruent with 18 modulo 63. Now we use this and basically put it in the other equation in the place of x. So 63k plus 18 congruent 34 modulo 91. So this also needs to be true, and obviously we subtract 18 because we can put on both sides of it, so it will stay true. So 63k congruent 16 modulo 91. Now there is like a theorem, I don't know the exact name of it, but I know that this, I think it's like Euclidean theorem of like you can only solve this 63 times k or x or any number or a number congruent with 16 modulo 91 if 63 and 91 largest common divisor LCD or like LCD is a divisor. So these two numbers LCD divide this number, so 16. We calculate 63 and 91's largest common divisor. It's 7, and 7 is not a divisor of 16. Thanks to that, this is not solvable. So there are no numbers that k can take and make sure this equation is true. And because of that, there are no numbers that give 18 when divided by 63 and 34 when divided by 91. So there is no solution for this task. Yeah. Let's say that if it was divisible, so like it isn't 7, but let's say it's a number at other number that it's 8. You divide the whole thing by that the whole equation of like not equation congruency with that number, and then you find what k equals. And then you take that k, so k it will look something like k equal congruent. No, so it will be like k, yes, congruent with I don't know, let's say 5 modulo 91. From that we know that k is 5 plus L times 91. We take that L and put it in the original equation, so here, so x equals to 18 plus 5 plus L times 91 times 63. You start to solve it, so like that will be x equals to 18 plus 63 times 5 plus 63 times 91 times L. You solve the whole and obviously you make it simpler, and then you get the equation for every single number that is both both congruent with 18 modulo 63 and congruent with 34 modulo 91. And then you just have to like start and calculate them from 0 to L0, L1, L2, etc. until you step over this 2021. I might look for a similar exercise and with actual numbers, but let's jump to this one, and then we can get back to here. For this one, decide whether those vectors in R4 which have two equal coordinates form a subspace in R4 or not. Now it's more of a using theorem exercise. You have to remember the rules of like subspaces for this and think using them. So in this case, if v, let's say v vector is in v, so no, let's say this subspace is called v, and let's say it is a subspace. If it's a subspace, then it has the adjective, but like, yeah, no. So so if it's a, let's say that if it's a subspace, then any two vectors inside the subspace, so any two vectors result, if you add them together, is also in the subspace. And also if you multiply it by any vector inside the subspace by a number, then the resulting vector also inside the subspace. So you basically can't exit it with addition or multiplication, nor subtraction. Using that and the fact that any, so like any vector that you choose, any two vector that you choose must stay inside the subspace. We first can try multiplying, but because if you start thinking about it, it would like mean that this sentence is true. Why? Because if you choose any vector that has the same two same coordinates, then you multiply it by any number. You multiply two numbers with the same number, you get the same number twice, so it won't work. So you start thinking with adding two vectors together. Let's say that there is vector 1 and vector 2, and if you add them together, you get vector 3, and vector 3 is inside of V. And also, obviously, V1, V2 is also inside the subspace of like V. Let's say V1 is 1, 2, and then 0, 0. Pretty self-explanatory. It has two of the same coordinates of like 0, 0, ergo it's inside of V. And let's say V2 is like 0, 0, that's 3 and 4. The first two coordinates are the same, ergo it's inside the subspace. Now, if we add them together to get V3, it's 1 plus 0, 0, but 1 plus 0, 2 plus 0, 0 plus 3, 0 plus 4. We get this vector of like 1, 2, 3, and 4. However, this vector does not have two of the same coordinates. That means V3 is not inside of the subspace. And because we left the subspace using simple addition, then it's not a subspace. So we proved that R4, where two equal coordinates form a subspace, is not true, not a subspace. Obviously, we could use like V.
Why is it not in the subspace?
Because the rule of the subspace is that have two equal coordinates, and that forms a subspace. and here by that they mean that like any v that you choose is like a, b, and then b and c, or like it could be also b again, but at least two of the same number, two of the same number must be inside of this like vector. And
So if V3 was 1, 2, 2, 4, for example, then it would be inside the subspace.
yes,
Okay.
yes, but obviously it can't be 1, 2, 2 because here it's a 3. So you, when you find a task like this of like decide whether these vectors form a subspace, then to prove it, then you either have to like add two together or multiply it with something. Let's say that you wanted to try in this case the multiplication, so like let's say v4 is 1, 2, 2, 3, and you want to multiply it with alpha, which is 1. Then v5, which is alpha times v4, will be 1 times 1, 2 times 1, 2 times 1, 3 times 1, which is obviously 1, 2, 2, 3. And looking at just this, it has two 2's, so v5 is also in the subspace and v4 is also in the subspace. However, as we proved, it's not actually a subspace because with addition you exit it. So you have to be careful when this type of exercises come up, and you have to, if you prove that it's a subspace with one of the two methods, then you have to check for the other. Because if that breaks it, then obviously it's just it was a false alarm. However, if you, let's say, break it or like prove it's not subspace with the first method of like, I don't know, adding or multiplying, whichever you choose, you don't have to prove it for the second one because you already proved that it isn't. Basically, it's an AND gate.
So, like, up in the example, did they give us the numbers or you just chose, like, randomly chose it?
You choose the number. You choose the numbers yourself of like what do you want to prove it with. Obviously, choose them first of all that it like makes the rule true. And I suggest choosing like small numbers because it's much easier to work with it. And when you are trying to prove that it's not a subspace, use one and zeros a lot because usually they break the rules.
So it's better to prove that it's not true than true.
Yes, yes.
Okay.
It's usually you have to prove it's not. Yeah. Hi. So yeah, you usually have to prove that it's not true, and it's also much easier to prove that it's not true because you just have to show an example, one example which shows that it's not true. If you have to prove that uh, it's true, then you have a much harder time because you have to either use a theorem or choose or prove it to every possible vector, which is kind of impossible. But to show another one, let's say in R4 is it subspace where the first coordinate is half of the second. It's like this type of like subspace is actually kind of common, or like in this exercises. So basically, I'm asking if v equal to a, then that's 2a, and that's like b and c, and choosing any numbers, this must stay true. And in this case, if you are trying to break it by adding two vectors together, then it's not gonna work. Or like not that simply, because if we choose v1 and v1 to be 1, 2, 3, and 4, and v2 to be 2, 4, 7, 6, then v3 will be the addition of these two, which is like 1 plus 2, 2 plus 4, yes, 3 plus 7, 4 plus 6, and you see that it's like 3, 6, 10 and 10. And by just looking at it, it looks like, yeah, it's true, because we just added two random vectors, and it still stayed true. And you can actually, I think, with any addition, you can prove that, yeah, it will stay the same. Because the reason for that is because it's like a to a, and we are adding b and 2b when we are adding two vectors together, and it will be like a and b, a plus b per 2a plus 2b, and it will be like a plus b per 2 times a plus b, a plus, and obviously it stays the same. However, we didn't prove yet that it's a subspace. We have to check then for multiplication. But for multiplication, you would get like, I don't know, a 2a b c times alpha, and it's then alpha times r, alpha times 2a, and you will see that even for multiplication, it should in theory stay true. So even when choosing so if you just choose like, I don't know, alpha to be 3, then it's 1 times 3, 2 times 3, 4, 3 times 3, I mean 3, and 4 times 3, it equals to 3, 6, 9, and 12. Yo, so on the surface, it still looks like present. It still looks good. Like 6 is 2 times 3. However, if we choose a if we said that any vector and any scalar or like multiplication. So if we choose v4, it's like v4 is v1 times beta, and beta, let's say 0. Then obviously it will be like 0, 0, 0, 0. Wait a second. Yes, and because of that, it's like 0, 0, 0, 0 is not in the subspace because 3 times 6, 2 times 2 times 2 times 0 is still 8 seconds. Yeah, I messed up now. It's in the subspace. It's in the subspace. Because a and 2 times a, if a is 0, it's 0. So it's also in the subspace. I lied to you. It's also in the subspace. Ergo, it looks like it's this theorem of like first coordinate is half of the second. It's true, and it makes it a subspace. And to prove it, it's like v is equals to a, b, and c. And if we multiply it by alpha, then it's like alpha a, alpha 2a, etc. And alpha times 2 alpha, you can obviously, because it's like a multiplication, you can cross out the alphas and you still get a per 2a, which is the original. So this actually forms a subspace. But obviously for that to prove, you have to write down this part of like a to a is basically plus b plus 2b is a plus b per a to a plus 2b equals to a plus b per 2 times a plus b, and also this part of like alpha times a per alpha times 2a, where you can cross out the alpha and you get a per 2a, because it's true, and that's why you have to like go through all the this like numbers and not numbers, letters, because obviously if you just choose random numbers, random vectors, and proved it on them that it's true, then then the teacher will say, but what if for a random combination in like, I don't know, 1,273 it's not true. So proving is always harder than denying it. Right now I got it, but yeah. And honestly, it was an accident. I wanted to prove that it's not true, but then I realized I wrote an actual existing subspace. Yeah, but it's like a small tip when you are trying to prove anything, work with small numbers and try to work with 0, because yeah, that's where or close numbers close to 0, because that's where where these rules usually break. Yeah, and getting back to here, I said that I want to show you at least another one. Give me a second of like where you actually there is actual solution of like
After that, can we have an example of basis?
basis. Oh, yes. Then let's go there.
Szia! Voltál már? Oké. Jó, csak mondtam, mert ki Discordra lesz.
How did I name it? Oh, ah. So let the vector a b c d part of R4. Give me a second. I want to find the. Yes, here. And from that, to be linearly independent, does it imply the set of vectors a, b, c, a plus b plus c plus d is basis in R4, RAT4? First, we need to show that these are linearly independent. These are linearly independent of like a, b, c, a plus b plus c plus d. And we know that they, a, b, c, and d linearly independent. And we also know that if they are linearly independent, then any number times a plus any numbers times b plus any numbers times c plus any number times a plus b plus c plus d is equal to 0. So alpha times a plus beta times b plus gamma times c plus delta times a plus b plus c plus d equals to 0. So if it is true, then they are linearly independent. And if we like break up the brackets and then order it, or put it in order, we can get like alpha times or alpha plus beta. No, sorry, alpha times delta, alpha plus delta times a plus beta plus delta times b plus gamma plus give me a second, delta times c plus delta times d. That's delta, just not d. Yeah, and it's equal to 0. And because a, b, c, and d is linearly independent, because of that, it's only possible if a alpha plus delta, so alpha plus delta is 0, beta times beta plus gives delta is also 0. And gamma times delta is 0. Gamma plus delta is 0, and delta is 0, because that comes from this fact of like A, B, C, and D is linearly independent. And from this, we get that A must be equal to B, must be equal to this, must be equal to 0, because delta is 0. And thanks to that, we know that these vectors linear combination trivial linear combination gives you the null vector. So that means that 0 times alpha plus 0 times beta plus 0 times c plus 0 times a plus b plus c plus d will give you 0. And thanks to that, it's linearly independent. Also, yeah, if it weren't linearly independent, then so one of these numbers is two of these numbers is something other than 0, because then that means you can actually because then that means two vectors are in the same subspace. Yeah, so we got here of like proof. We proved that it's linearly independent. Of like this is linearly independent. And thanks to the theorem, in a errad k yes, in a errad k k k linearly independent vector is base. Yes, independent. So in errad 4, for independent vector is a base. So that means this vector combination is a base in errad 4. For that this conclusion for you to get, you have to obviously prove that it's linearly independent, and it's always when you are proving that something is linearly independent, you try to find the which linear combinations of the vectors give the null vector. That's what we wrote down here of like A times alpha times A plus beta times B plus gamma times C plus delta times A plus B plus C plus D equals 0. And yeah, obviously, if like all of them is 0, it will be 0. If you can find any combination that will give you a number other than 0, then it's not linearly independent. And these of like alpha plus delta must equal 0, beta plus delta must equal 0, gamma plus delta must equal 0, delta must equal 0. That comes from the fact that A, B, C, and D just in itself is linearly independent. Yeah, that's basically how you solve it. But you need to like write more than I wrote of like every single step that you take. You have to write it down because uh, uh, they give points for not the solution, but how you got to the solution. Or yes, not they give points not on the answer, but on the solution of like how you solve the problem. That's the better way to phrase it. Yeah.
How much more like do I need to write?
I will send you of like or not you. Or I will send in the chat in a file, a zip file. It has the last year's or like no previous year's midterms and with so with with solutions and next to solutions that is like of how many points each sentence of like each step words, so you will see, but it's like here they like give you a point for writing down that in error 4 this is base because it has uh, four vectors and they are linearly independent, and it's like basically 3 points that you write this sentence down. But yeah, well, I hope I helped. I will upload this also.
Okay, thank you.
Do you have like any questions that I?
You said you'll show me an example, like for the number theory.
Could you repeat? Sorry.
You said you'll show an example before I asked you about the basis.
Oh yeah, I know. Let's go there. I can find it. Give me a few seconds.
Okay. And where will you send the zip file?
In WhatsApp.
Okay, thank you.
I actually think I already have one that I solved. Oh yeah, yes. So now I will, yes. So this is this example. How many integers are there between 1 and 10,000 whose last two digits in the decimal system are 34 and whose last digit in the hexadecimal system is e? The hexadecimal system is a numeral system of base 16. The e denotes to the digit 14. Now, while it sounds like, I don't know, pain, it basically just asks if x or n, which numbers are gives 34 as a remainder when you are dividing by 100. This comes from last two digits into the decimal system are 34, and also at the same time give you 40 as a remainder when dividing by 16. That comes from this part of like the last digit is e in the hexadecimal system. But let's just focus on this part. So n congruent is 34 modulo 100 and n congruent 14 modulo 16. N congruent 34 modulo 100 means that n is a number which is 100 times k plus 34. And we go here and we write the second congruent in the place of n this expression. So 100k plus 34 congruent 14 modulo 16. We subtract 34 from it, so we get 100k congruent minus 20 modulo 16. This and now we check that we checked last time of like 100 of like this number, and what the modulus largest common divisor can be divided by this number. So it's or it's a division of this number. 116's largest common divisor is 4. Here I calculated it just like last time, or like the yes, and 4 is a divisor of minus 20 or like 20. That means we can continue because of like the way we used it last time. Minus 20 is all so we make both expressions simpler. 100 is 6 times 16 plus 4. Minus 20 is plus 2 times 16, it's 12. So we get 4 congruent 12 modulo 16. Now we divide the whole expression with by 4, and because it's like dividing modulus, we also have to dividing congruency. We also have to divide the modulus by the moduluses and divisors largest common divisor. So 4 and 16's largest common divisor is 4. So we get k congruent 3 modulo 4, which is still the same expression of like here, but like it's instead of 4, it's 16, it's 4. So from that we know that k equals 4l plus 3, because 4 times l plus 3 will always this equation will give you all the numbers that congruent with 3 modulo l modulo 4, and now you take this k equals 4l plus 3 and put it back here instead of this k, and we get 100 n equals, or like the number equals to 100 times 4l plus 3 plus 34. It's like and you make the expression more simple. So from 400l plus 334, this equation will give you all of the numbers that give 34 as a reminder when divided by 100, and 14 when divided by 16. And now you just have to like find all of the numbers of which else is it true for no, sorry, so all of the else it's true for, so like L1, L2, L1 million. However, the original question was between 1 and 10,000, and how many integers, so you have to find which L is the last L, which will give an answer of like below 10,000. You can start it. You can find this by starting at 10 of like 400 times 10 plus 334, you will see that it's like not enough. You double it, you get 20, it's like closer. You basically find this L by trying out different integers. But before that, it's like the more important part is this of like remembering that you have to first make sure that this is solvable, because if you can't divide it by this, that it's not solvable. Then you divide it, you get this expression of like k congruence 3. You write down the common equation for finding all of the answers, and then you put this back in the original one, and then you get the equation for all of the numbers. Yeah, and that's it. Like, yeah. This one is also I think somewhere up in the group, so you can also check this out if you want to. Yeah, it's basically only from the first consultation. Yes.
Like for example, this one, the equation of line,
Sorry.
like down the equation of equations of lines. I just saw.
Oh.
No. Yeah.
This.
Yeah, this one. Like, can we use, for example, matrices?
Sorry, could you matrices or what?
Yeah. Yes. Can we use it to find it?
No, I don't know. No, I don't think you can. Or like, I don't really understand the question of like.
Like, can we use matrix?
To find what?
Like substituting the.
Oh.
Like making an augmented matrix.
Yeah. I think you can. You can. Yes, you can use an augment. Yeah. Yes. You can. I see now the question. Yeah, you can. If you can write it up correctly, then you can.
Okay, thank you.
You're welcome. But yeah, that's all I think I could help for now. I know that you are writing from the first one, so I won't bother with like with this one, because it's like it's definitely in the second. It won't be in the first midterms retake. So yeah, I will upload the notes, and good luck if you don't have any other question.
Also uploading the zip file.
Sorry.
The zip file.
The zip file. I will. Of course, I will also upload that. It's in Hungarian, but yeah, you have to translate it, and then you can use it. Okay. All right. Goodbye.
Thank you so much. Goodbye.
You're welcome.
Bye.